So today I'm going to talk about modeling of crystal growth. So this is very much work in progress. It's a project that I'm doing together with Espen and Camilla, and so far it's been colloquium based, I would say. So we meet every Tuesday at 10, and we discuss what we have managed to do so far and what we should do. It's very nice way to work. It's kind of a fun project. So on this first slide, I put up a nice picture, and it's the only nice picture I'm going to show. So I thought I should have one picture of a rock, but it's kind of showing a motivation for this work. So it's related to crystal growth in pores, and this pattern that you see here, it's caused by salt crystallization inside the porous rock. So this happens. This is something that you see, for instance, often near the sea, where you have salt water being washed up on the rocks, and then it goes into the pores, and when it dries, then salt crystals grow, and there's a self-localizing effect that makes these cavities grow. And how they grow is that you have crystals growing inside the pores, generating pressures, and then pieces of the rock cracks off, and you get this kind of pattern. So what we're interested in here is the process of crystals growing inside pores. So I'll try to talk a bit about the motivation, or why we started this project. And it's I'm sure many of you have seen me show this picture before. So this is related to some experiments that we've done on the so-called force of crystallization of crystals. This is a picture from experiments that, among others, François Renard have done in France, where again you have, in this case, a limestone, and you have a solution of sodium chloride, so a salt that goes into the pores of the rock. And where it evaporates, you get an evaporation front here, and you have growth of salt crystals, and you can see that they actually break this rock apart, and you get crystal growth inside here. So the reason why the crystals manage to do this is that when crystals are growing from a supersaturated solution, there is kind of an inherent possibility that they can grow and they can push on the weight. And this was shown experimentally, for instance, in 1905 by Becker and Day, who kind of did the simplest thing that you could do. They took an alum crystal, put it in a beaker between two glass plates, put a weight on top, and then had it in a saturated solution, which was open to air, so that you had evaporation of water, and this solution became supersaturated, and this crystal was growing, and they could observe that it was lifting up this weight. So this is kind of the reason why you get forces that manage to crack open things. So just how this happens is not that easy to understand, and it's not that well understood. So one of the things that has to be taking place here is that there's not actually contact between the salt crystal, which is this, and the glass, because you have to actually grow the crystal kind of between the crystal and the glass to be able to lift it up. And you can only transport things through water in this case. So you have to transport new material to the surface of this crystal for it to be able to grow and lift itself up. It's like if you were building a tower of Legos and you wanted to build it taller, you have to actually be able to put the new Lego pieces on top. So there's a question of what maintains this fluid film between here, what maintains the transport, why do things want to move from solution and into the gap between here and grow there? Why don't they just grow somewhere else? So just schematically, the crystal, so this is my crystal, it's growing between two plates from a supersaturated solution. And on this side, it can grow freely, free phase growth. And then on these sides, we could call it confined growth. So it's growth, but it's kind of limited by this confining wall. And then since you get this cavity forming inside, so this is something that was observed in 1905 and also later, that it tends to not grow on the whole surface, but you get this cavity formed underneath. So for some reason there's no growth in the middle, there's only growth on the sides. And this is then probably caused by some kind of balance between the flux of ions in from the bulk solution and the flux of ions that get incorporated onto the growing surface. So there's an interplay between growth and transport. And I've talked about these experiments that I did before, and I'm going to just show you a few details of them now, and then you can, don't expect to kind of understand everything that we did, but you can ask later if you want. But kind of just the basics. We did some experiments where we had a crystal growing on a glass plate inside a beaker of a solution, of a supersaturated solution of salt. And it was in a temperature-controlled bath, so the temperature was constant and we could know the concentration and everything. And then on some of the crystals we put a weight, or we clamped it so that there was a force on the faces of it. And then we could take the crystal out and we could measure the size of this rim that had formed. And in some cases it grew this kind of staircase rim, and we could measure the dimensions of that. And the reason why we did this was that there was a theory that was proposed many years ago that relates the width of this rim to the applied stress on the crystal and the properties of the thin fluid film. So we wanted to see if we could learn something about the properties of this thin fluid film by measuring the width of the rim at the different applied stresses on the crystal. So then we used white light interferometry to get to measure the topography of the crystal. So this is less than a millimeter on each side, and then this is the topography, and it's very exaggerated in this direction. So just a line plot along the rim here, like this. So this is micrometers and this is millimeters. So you see that there are some big jumps in topography. The height of this rim varies by many micrometers. And also when you look closer, this is a typical section of a rim. This is also along one of these rims. So we had thought when we started this that the rim would be smooth because it's carrying the whole weight of the crystal. But instead we couldn't manage to grow any crystals with smooth rims, so it wouldn't kind of even out to distribute the load. It would tend to just grow as a rough surface at all of the loads that we managed to apply on the crystal. So then there's the question of how do we understand this? What's actually going on this growing surface? And then we have to learn a bit more about how a crystal actually grows. Because relatively, or under many conditions, crystals grow in a faceted way. It means that, as this is something that you see in the rocks all the time, that crystals have a certain shape, and you've all learned about this, that they don't just tend to be round. They want to minimize their surface energy, but they don't do it by just minimizing the surface area. They do it by growing on surfaces that have less energy. And you can think about it as the crystal being composed of square, if you like, building blocks that have less energy if they have more neighbors. So this guy sitting here on what you can call a terrace. So this is a crystal, and it's composed of layers. And these guys that you can call add atoms. So there are atoms that are absorbed on a flat surface. They don't have very many neighbors. They just have the neighbors underneath. So they're not in a very energetically favorable position. But if they manage to get over here to sit next to this edge, then they get more neighbors. And if they manage to attach at this kink, then they have even more neighbors and they're more happy. So when the surface is growing, if you imagine that you have a solution of particles here, then you have the movement of particles in the solution, and you have them attaching on the surface, but then they will also be moving around on the surface and finding the most favorable position to sit in. And this is what makes this flat faces on the crystal. So the shape that the crystal ends up getting depends on the driving force, which is then a measure of how many extra growth units you have in the solution. So if the driving force is low, then atoms very seldomly manage to attach themselves on the surface, and once they do, they have plenty of time to move around and find the best site to sit in, and you get very flat faces. In fact, at very low driving forces, atoms never manage to kind of meet each other and form new terraces on existing terraces. They only manage to grow where you have defects in the lattice, so that you already have a kink or an edge to attach to. So this makes this kind of very flat faces, and they tend to grow from the middle and kind of propagate outwards, or from defects that are located near the middle of the face. Then if you increase the driving force, so you increase the number of particles in the solution, or how often they attach to the surface, you move into this regime where it's possible to have two-dimensional nucleation. So it's possible for these atoms to meet and attach to each other and make new terraces on already flat surfaces. And then what happens is that if you have, say you have a square crystal, and it's sitting in a solution, so transport is driven by diffusion to this crystal. Then you have a diffusional field around it, so these are contours of equal concentration, and they tend to be round, because that's how diffusion works. So when you get closer to the crystal, it turns out that you have higher concentration at the corners of the crystal. And this means that it's easier to start new steps or terraces near the corners, and you will tend to grow faster also near the corners. So you will tend to grow from the corners inwards and slow as you move inwards, which creates this kind of morphology. It's called a hopper morphology of crystals. And we think this is actually what creates these steps that we see on the confined crystals that we had in the experiments. Because they have, in that case, it's not because of the diffusional field in the free solution, but it's because ions are only transported from the bulk solution and into this thin film, and they're kind of used up before they reach the center of the crystal. If you increase the driving force even further, then this effect of points sticking out being exposed to higher concentration becomes more and more important. So then this corner is sticking out more, and if it's easy for atoms just to attach to its surface and stay there, then it will tend to grow more in the corner, and then it's exposed to even higher concentration, and it grows more, and then you get into this very rough regime and this kind of dendritic growth, and you get to very high driving forces. So this is something that would be nice to model. If we could make a numerical model where we could put a particle into some geometry and then study the combined effects of surface kinetics and transport, then we could see how how a crystal is growing inside confinement. So we've seen that the surface morphology, or the morphology of the crystal, is governed by the growth kinetics and the transport of solutes, or growth units, to the surface, and also probably by surface stress. So if you move very close to a confining surface and you're supporting, you're applying a stress on the surface, then this must also be affecting the growth somehow. So it would be nice to construct a numerical model where we could study the effect of these parameters and then compare with the experiments, see if we can reproduce what we see, maybe get some explanation of why this roughness evolves, and also see, so when do we actually clog up pore space? When do we stop transport, and when do we keep having this continuous thin film, for instance? Is it so that there's a crossover to a smooth surface if we just increase the stress enough, so that if a crystal is supporting a much higher stress that we were able to do in experiments, would it then become smooth? That could be. And what actually happens at these contact points? That's kind of the most difficult question, but also, I guess, the most interesting. So what happens where we actually have the high load? So in order to do a numerical study of this, we have a problem, because this is something that happens at the molecular scale. So a typical approach would be to use molecular dynamics. So you have your molecules, or atoms, they interact with some potentials. You give them their velocities according to temperature, and they move around, and they interact, and they evolve in a very correct way if you put in the correct parameters. The problem here is that the time steps that you have to have in your simulation is about 10 to the minus 15 seconds in order to resolve the atomic vibrations. And it means that you can't really simulate very much more than a microsecond. I guess it depends on what you're simulating. But anyway, what we want to model takes much, much more time. It takes seconds, at least. So it wouldn't be feasible to do this while resolving all the atomic vibrations. So, and actually it doesn't, maybe we don't need to model all of the vibrations, because the events that we're interested in is the diffusion of particles in the solution, and it's the movement of particles on the crystal lattice, and the absorption and desorption of particles. So if you run, we have this fantastic picture here, which I didn't draw myself. Actually, I copied it from an article. But this is showing, we could say that this is a particle that wants to diffuse on a lattice. So this is a particle that can sit in several positions of energy minima. He said this is a nice position to sit in because it has a low energy due to the neighbors it has on the lattice. It could choose to jump over here. It would also be a minimum in energy, or it could jump over here. And if it jumps, that's diffusion, and that's interesting. But what it does most of the time is just moving around in here. So if we just know how often it manages to escape from one of these wells and go into another well, we can just take those events. So these infrequent but interesting events, and we can forget about all of the stuff that we're not interested in, and then we can do much longer simulations. So this is what I'll try to explain as the Kinetic Monte Carlo method, where we look only at the significant events and we use the appropriate rates for all of these events. Please ask along the way if you have questions, by the way. Just to show you an example, these are very pretty pictures from a Nature paper in 2005. So this group has studied the growth of urea crystals from 2 different solvents, water and methanol. So what you can do with molecular dynamics is typically something like this. So they've looked at 3 different crystal phases, and they can resolve then the interface between the solution and the crystal. And when they run the simulation, they can see how often an atom will jump from here to here, or how often an atom will move on the surface, and so on, depending on the position it has, how many neighbors of different types that it has. But you don't really get any information on what the crystal will look like, because this is much too small. But what you can do is you run the simulation for some time, and then you just count how often different things happen. And that's the rates that you will use. So you say it's you can see that it's much easier to move this particle than that particle, and this takes time 100 times as often as this, and so on. And then you use this as an input in your large-scale Kinetic Monte Carlo model. So in this case, you're taking all the rates from here, and they run large systems. And they managed to show that, so this is 1 micrometer, so this is really quite a significant size of a crystal that they've grown. And they can compare with microscope pictures. So it shows that growing from water, you get this kind of needle-like geometry of the crystal, because the growth rate of this phase is much faster than everything else. Whereas when you grow it from methanol, it's these phases that dominate. This phase is not really showing at all, and you get a much more blocky geometry, and it's just what you see in experiments also. So they're really, just by taking really just a few numbers from these simulations, they manage to replicate what happens in nature on a much larger scale. So the way this works is first you create your system, and then at each time step you draw a random number. That's the Monte Carlo algorithm. It's named by the casino in Monte Carlo. So it's drawing numbers at random and doing things. So you pick something at random that will happen, you increment the time, you update, and you go through this loop. And this is how you evolve your system, and then I'll go through a few of the steps. So the input, of course, determines what comes out at the other end. So one thing is that you have to define your lattice. This is easiest if it takes place on a fixed lattice, but it can be done without a lattice also, but it takes much more computation along the way. But you have to decide where your particles are, where your initial crystal is, if there's an initial crystal, etc. You have to decide what happens at the boundaries, obviously. And then the most important part is that you have to identify all the possible microscopic processes that might be important in this case, which is not always that easy, but it's the most important thing. And their transition energies, or their rates. So to do this very accurately, you can do molecular dynamics simulations, as I showed you. Then you have to know the potentials for these different atoms, but you don't really have to know everything that's going to happen with it, because it kind of comes out from the simulations. Or you can use transition state theory, which I don't really know what it is, but or how it's done. But usually, or it's you can simplify this quite a bit. So so just to try to show you, if we imagine a very simple energy landscape like this, and we wonder if this particle, what's the rate of this particle moving out from this state to this state. Then it has a certain energy where it's sitting, And in order to pass to the next state, it will have to pass some barrier, some kind of saddle points in the energy landscape. So if we know the energy in each of these different positions, without really caring about the shape of this, so the rest of the energy landscape, we just care about the saddle point and the positions that the atom can sit in, then we know the energy difference between these 2 points, and then we know that the rate is an exponential function of the size of the barrier divided by the temperature, and then some kind of a rate of vibration rate. I'm going to say the wrong thing no matter what I say here. It's kind of some kind of typical rate, some number. In my simulations, it's 1 so far. Then what's nice is that this often works. That you just assume that the energy in the different points just depends on how many neighbors you have in those different points. So for instance, this is an atom which is going to diffuse to this point. So first it's sitting in this position, and it has, this is a 2-dimensional system, so it has 3 nearest neighbors, which gives a certain energy contribution. So then the energy that it has is then the number of nearest neighbors that it has times whatever energy contribution comes from a nearest neighbor. And then you can choose to include next nearest neighbors, which would be this, and this. So that's the number of next nearest neighbors times the energy of the contribution from the next nearest neighbors. And then you can go on if you want, but it's often just looked at these, but it can also be useful to look at the next nearest neighbors depending on the system. So that defines the energy we're at, and then you need to know the energy at the saddle point. So the easiest thing to do could just be to say, well, that's halfway between the 2 positions I'm interested in, and then I just say that these 4 neighbors are the nearest neighbors to my saddle points, and so the number of saddle point neighbors give me a saddle point energy contribution. So this is all I need to know to calculate the rate of moving from here to there. So if I know the position, essentially if I know the position of all of my particles, and I know these 3 energies, then that's kind of all I need to know. So in 3 dimensions, it's more fun to do these things in 3 dimensions. It's more complicated, obviously. There are 6 directions you can move in. This is a guy who has no neighbors, so it's just a random walker in solution. He has no neighbors anywhere, so the rate will be 1. And then this rate is what everything else then is normalized to. So if he attaches to 1 other atom, he's got 1 nearest neighbor. And if he tries to move in this, or this direction, he has 1 saddle point neighbor, which then gives 3 different rates. So this direction he can't go, so that's 0. And then if he just moves straight out, he's got 1 energy. The energy from, he's got 1 rate, and the rate for moving in these directions is a bit higher. It's a bit easier to kind of move along a neighbor than to just detach. So this would be then an add atom, where it's much easier to diffuse on the surface than to detach and move into solution because of the numbers of neighbors you have. Or if you were at the kink site, you have even more neighbors. So here it's kind of easiest to move this direction, and then it's a bit more difficult to move in these other directions, etc. So if you manage to keep track of the neighbors, then there's quite a rich dynamics that you get out because there's many different combinations. So then for each time step, you need to decide what you want to do. And there's two different methods to do this. So the first is called the null method, and it's kind of the easiest. It's just for each time step, you pick a random number that gives you a site. And you go to that site, you ask what can happen here. It could be to stand still, or it could be to move. And then you calculate the rates, or the inverse of a rate would be a probability. So you calculate the probabilities of all these different things happening. And then you choose a new random number, and you use that to decide what you're going to do. So you go somewhere, you ask, do you want to do something? And then you might move, or you might not move. And you do this over and over, and this is how you evolve your system. So the good thing is you don't have to calculate very many rates at each time step. There is at maximum 7. You can move in 6 directions, or you could stand still. But you spend a lot of time doing nothing, because most of the time the particle might choose to just stay where it is. So in many cases, it's better to use another method, rejection-free method, where you're sure that one thing is actually going to happen at each time step. So then what you do at each time step, you calculate all the rates of everything that could possibly happen in the system. So that's the number of particles times 6, because you don't care about the standing still part. So that's how many rates you have to worry about for each time step. Then you pick one random number, and you choose one of these events, and that's what's going to happen. So the good thing is that at least something happens at each time step, but the bad thing is you have to keep track of all the events all the time. So when you're using this rejection-free method, you have to have a nice way of keeping track of the rates and choosing which event you're going to make. So if this case are rates, so you have n times 6 rates to keep track of. So if you imagine having them all in a vector, or in a kind of measuring stick, and then the size of each of these boxes is the size of the rate. So if you have a high rate, if it's probable that it's going to happen, you kind of get a big box, and if it's very improbable, you get a small box. And when you draw a random number to pick a random position, you probably happen at one of the big boxes, but sometimes you get one of the small boxes, and this is how you evolve. And in practice, you make a cumulative sum, and you get the computer to search through this cumulative sum until it finds the right process. Of course, this could take a long time because you have to go through a lot of a very long list to find the right event. So then you have to come up with a smart way to do this. And there's a number of different ways that you can split up your vector into tree structures and use them to search, and it can really speed up what you're doing. In addition, you have to increment the time. And what's kind of nice about this is that the time increment for each iteration, it depends on the total number of or rates of stuff that can happen in your system. So if, for instance, if you have just a solution of random walkers, they will have a high probability of moving, and so there's many high rates, and the total time that you can move for each time step will be short. You have to resolve time into many short time steps. But if you have things that are not going to do very much, then you use long time steps. And this kind of comes out naturally because the time you advance clock by at each time step is just the inverse of the total, the sum of all the rates. And then you have to, of course, when you move one particle, you have to move it on the lattice, and you have to update the probabilities of everything that could happen with the neighbors of that particle. So you have to keep track of every particle that's affected by this particle. And this could also be done in kind of smart ways. You can either move around in your big grid and find out who's affected, or you can use some kind of smart tree structures that we started discussing today, which sounds promising. We have to figure out how to do it. That could make this also go faster. So then I just want to show you some very preliminary results of this, because we still have some ways to go to put the code together. This is a simulation that Espen did a while ago. So you can see the ingredients. You have all of these particles that are free, so they just move around as random walkers. So that's the diffusion of particles in solution, or in a gas. I guess it wouldn't really, you can't tell the difference in this case. And then this is the crystal, so they can sit down on the crystal lattice and they can move around, and you see that you get these steps forming. And in this case, you have a supply of particles from this side, so you have most growth here. So you will start steps at this side, and then they will move inwards and kind of slow down. So you will get this kind of staircase structure forming from this side because of the transport. And then these are some more recent, but not so nicely visualized simulations that I did in MATLAB. I couldn't really figure out how to do it in 3D, or how to visualize it in 3D. So I just have to. Can you see the blue dots? Yeah. Okay, they're not that interesting actually. So this is a 150 by 150 by 150 lattice, and what I did was I just summed everything in this dimension. So the warm colors are more particles. So in this simulation, I start with a spherical particle in the center and a bunch of random particles around it. And then so this is 1,600 particles, and it took my laptop some hours to do this, without implementing any smart tree structures or smart methods of searching. So it's periodic boundary conditions, and it starts at a quite low temperature, so it's easy for the particles to stick together. And then at the end, the temperature is increased just to see what would happen. So then you see that what happens is that they stick together, and then you have this coarsening process. So the smallest particles disappear, and you're left with bigger and bigger particles. So each time a particle, yeah, and then the temperature was increased and everything melted again. So, but what you could also see on these plots, this is time, and this is the energy. So it's just summing the energy of all the particles in the system on a logarithmic scale. So I'll show it again, but it starts with the energy going down because everything sticks together. And then each time one of the small particles disappear, so evaporate or melt, the energy goes down a bit. And the time steps become longer when the particles are sticking together because not so much happens. But each time one disappears, you release some random walkers and the time steps become short again. And then at the end, the energy goes way up and the time step becomes very, very short. So I'll just show it one more time. So the energy kind of moves down in steps, and the time scale becomes longer. And then I did a couple of runs where I kept a constant concentration. So I made a system which has periodic boundary conditions here, and then in these phases. So it's so you start with a crystal in the middle, which means that you have a face to grow on here and another face to grow on here, and then there's a constant concentration on these two sides. So you will keep having particles that kind of move down and attach to the crystal faces here, and they will be growing. And this is just plotting these two crystal faces that are growing, and different colors are different layers. So see that when the concentration is quite low, then you tend to grow almost one layer at a time. So when you start putting down particles, they really want to go and find positions where it's favorable to sit. They don't start nucleating new spots on the surface very easily. Whereas if you increase the concentration a bit, then it's much easier to nucleate on existing terraces, so it becomes more patchy in a way, so kind of more rough surface. And just to compare, at roughly the same time, it's not really the same time, but it's almost the same time. If you have a low concentration, it's not grown very much. If you have a high concentration, it's had time to grow much more and grow more layers. And that was pretty good timing, I would say. And if you have some questions, if you want, I can show movies of the stuff that Espen did, but I can't show them in PowerPoint. So thank you for your attention.